In this lesson, we're going to learn a little bit about probability. And what we'll do is we'll focus on the concepts of probability right now. Later on, we'll apply some of those concepts when we get to things like hypothesis testing and confidence intervals, and we'll see how those apply. There's also a few problems that are real basic probability questions in the practice problems in the homework that you'll have due. So, just make sure you have a fundamental working knowledge of some of these probability ideas and concepts. And we'll learn about these primarily through examples. So the first thing that we have to think about are the approaches to probability. We have a classical approach, which is really based on equally likely outcomes. Typically, we use classical probability when we play games like Yahtzee or Chutes and Ladders or cards like euchre or something like that. Because we have a finite number of outcomes and we can figure out how many cards are left in the deck and everything else. So we can look at that in terms of equally likely outcomes. Empirical probability, however, is a little bit different. This is based on relative frequencies. So with empirical probability, basically what we're doing is we're gathering data over a period of time, and then we're using that data to help us define a probability of something happening. So there's some rules for probability. Rule number one is any probability has to be non-negative. In other words, it has to be greater than or equal to 0. And we could go a step further than that. An individual probability has to be between the values of 0 and 1. If we have a probability of 0 for an event happening, that means it's not going to happen. If we have a probability of 1, that means that event is definitely or 100% chance that event is going to happen. Generally, our probabilities are somewhere in between 0 and 1 for an individual event. Rule number two is basically saying that if we add up all the probabilities for the events, then the sum of all those probabilities has to be 1. So that's what we're looking at with those two main rules. There's other rules that we're going to get into in just a little bit that deal with multiplication and addition, and we'll cover those in just a minute, but those are two things that we have to think about before we get there. Now, there's one last thing we have to take a look at, and that's understanding the difference between classical probability and empirical probability in terms of how we calculate that. In classical probability, we're dealing with things, like I said earlier, like dice or cards or other things like that. So if we were looking at the probability of drawing a king, for example, it would be the number of favorable outcomes or the number of kings in a standard deck of cards over the total number of possible outcomes, which would be all the cards in the deck. So in that case, we have 4 kings in a standard deck out of a total of 52 total cards. Empirical probability, however, is a little bit different. We're collecting data over a period of time, and we're looking at the observations that of an event that we're interested in out of the total number of observations we made. So, for example, we might use this if we're in the insurance industry and we're trying to calculate the probability that a male will get in a car accident. And the reason we might do that is because we want to base their risk or their insurance costs on how probable it is that they get in an accident. So to do this, what we might do is we might take and collect data for maybe a few months, look at all the males that we have insured, and then out of all those males that we have insured, we look at the number of individuals that got in an accident, and then use that to calculate our probability. So it would be the number of times that the event actually occurred, a male got in an accident, over the total number of observations that we've made. So generally, we're using empirical probability for a lot of stuff, but I think the classical probability helps us understand the empirical probability a little bit better. Now, when we calculate probabilities, there's a couple key words that we need to be able to associate with the operators. The first key word is the word or, and that indicates that we're going to be using a rule for addition. And the other key word that we have is the word and that's generally indicating that we're using a rule for multiplication. So think or, addition, and multiplication. So let's take a look at a few examples. These are going to be examples using a deck of cards or a die. So maybe to start off, let's talk about a standard deck of cards. So in a standard deck of cards, we have 52 cards in a deck. We have 4 different suits. We have hearts, we have diamonds, we have spades, and we have clubs. We have, red and black cards. And I'm trying to think if I'm missing one of the characteristics. I think those are the main things, okay? So if we have that in mind, that'll help us with answering some of these questions and going through and understanding it. So we're going to start off with the special rule of addition. So the question that I have is, what is the probability of drawing a king or a queen from a standard deck of cards? When we have the word or, we want to draw one of those cards or the other. So you could simply grab a deck of cards and you could count up all the kings and queens, and you would see that there's 8 of them out of a total of 52 cards. Well, when we talk about this in terms of using the word or, remember, or means addition. So this is really the probability of a king plus the probability of drawing a queen. And when we think about this, there's 4 kings in the deck out of 52 and 4 queens in the deck out of 52. And when we do the addition, remember, we add the numerators. They have a common denominator already, so this is 8 out of 52. And when we express a probability, if we express it as a ratio, it is going to be in the lowest common denominator. So we're going to have 2 over 13 if we reduce that, or we can express it as a decimal of 0.1538. That's between 0 and 1. Or if we want to express it as a percentage, we can do that as well. This would be 15.38%. Okay? Now these events right here, these are what we call mutually exclusive events. So we have the kings and the queens. They have nothing really in common that we're interested in terms of calculating out this probability. So this Venn diagram right here, the rectangle is really representing the event space, which would be all 52 cards. This circle represents the kings, and this circle right here represents the queens, and there's exactly 4 queens, 4 kings, and then the remainder of the cards are out here in this white space inside the rectangle. Now the general rule of addition might look like this in terms of an example. We might ask the question, what is the probability of drawing a king or a heart from a standard deck of cards? Well, with a king and a heart, they have something in common. There is one card that is both a king and a heart. So when we do this, we're applying what's called the general rule of addition. So we would take the probability of a king plus the probability of a heart, and then we have to subtract off the probability of a king and a heart. And the reason we have to do that is because in this group right here, we're counting up the probability of drawing a king, which is 4 out of 52. This group right here includes that king of hearts. Over here, when we count up the number of hearts, we find that there's 13 out of the 52 that are hearts. If we add those together, we'd end up with 17 out of 52 because we double counted the one card, which is the king of hearts, which is in both of those groups. So you can see the math right here worked out. Again, when we do the addition and subtraction with this, we'd end up with 16 out of 52. And if you took a deck of cards and pulled out all the kings and hearts, you'd find that there's 16 of them out of the total of 52 cards. That reduces to 4 out of 13, or 0.3077, which again could be expressed as a percentage. 30.77% chance of drawing a king or a heart. Now, the Venn diagram down below right here has 2 circles. The smaller circle represents the kings because there's fewer of them. There's 4 of them. The larger circle represents the hearts because there's 13 of those. And then this intersection right here where they overlap each other, that represents the one card that is both a king and a heart. So with these, we have what are called non-mutually exclusive events, or sometimes also referred to as joint probabilities, because we're talking about this area right here in the Venn diagram. The next rule I want to introduce is the rule of complements. So when we talk about complements, sometimes it's easier to calculate a probability if we know something else. So the question that I have is, what is the probability of not drawing a king from a standard deck of cards? Now, I know most of us could figure this out in our head pretty quick, but the easy way to think about it is when we say the probability of not drawing a king, it's really 1 minus the probability of drawing a king. That's kind of the rule applied right there. Now, the notation that we typically use is this right here, the probability of a king with a superscript of a C, meaning the complement of that. And again, I said 1 minus the probability of a king, which is 4 out of 52. And the reason we're doing this is because it's easier to count up the number of kings than it is to count up all the other cards. So 1, if you recall, this can be changed to 52 out of 52. That's equivalent to 1. And then this would be 4 out of 52 right here. So 52 minus 4 is 48. We have a common denominator right there since we're doing subtraction. So that would be 48 out of 52, or it could reduce to 12 out of 13. So there's a 92.31% chance of drawing a card that is not a king from the deck of cards, which that would make sense because there's more cards in the deck that are not kings than there are kings. Now the general rule of multiplication. There's two rules of multiplication. We'll start with the general rule. This is sometimes called conditional probability, and we'll get to that in just a minute. But the question I have is, what is the probability of drawing a king and a queen from a standard deck of cards? Remember, we're talking about drawing both of those cards. Or meant one or the other. That's why we were using addition. And represents we're doing multiplication because we want to do both of those events. So when we do this, the probability of drawing a king and a queen is the probability of a king times the probability of drawing a queen, given that we drew a king in that first draw. So when we do this in terms of the multiplication, we have 4 out of 52 for our probability of drawing a king, but we pulled that card out of the deck. So our deck is actually a little bit smaller. So when we talk about the probability of drawing a queen, we have to make the assumption that that first draw was a king, and our deck now only has 51 cards in it remaining to draw that queen from. So we have 4 out of 51 for our chances of drawing a queen. When we do the multiplication on this, this would be multiplying numerator by numerator would be 16. 52 times 51 is 2,652. This reduces to 4 out of 663 if you wanted to reduce it to a fractional value, or a decimal value of 0.0060, or 0.6% chance of drawing a king and a queen from a standard deck of cards. So like I said a little while ago, this is called conditional probability because drawing the queen on the second draw is conditional on the fact that we drew a king on the first draw. All right, now it's time for the last rule, which is the special rule of multiplication. And the example that I have is using independent events. And this is really important when we deal with the special rule of multiplication, is we have two independent events. So the question I have is this: what is the probability of drawing a king from a standard deck of cards and rolling a 6 from a standard 6-sided die? So when we write this out, this is simply the probability of drawing a king times the probability of rolling a 6. Now it doesn't matter. If I draw a card from a standard deck, it's going to have no influence on what I roll for that standard die. And the same thing if I flip it around. If I roll the die first, that's not going to influence drawing any card out of the deck. So when we do this, the probability of drawing a king is going to be 4 out of 52. A standard 6-sided die, there's exactly 1 6 on a standard 6-sided die, so that's going to be 1 out of 6. We multiply those, so that's going to be 4 out of 312, or we can reduce that to 1 out of 78, or 0.0128 as a decimal, or 1.28% of rolling a 6 and drawing a queen. So in this case right here, we have events A and B that are independent of each other. Now sometimes what some texts will do is they'll write this out using the general rule, and instead of the probability of just roll a 6 right here, they'll say probability of roll a 6 given that we drew a king on the first draw. Well, when they're independent, this given statement or this conditional statement right here reduces to just the probability of A because they're independent. That event B has no influence on A, so that's why this is equal to the probability of A. And then the probability of B given event A is equal to the probability of B. So hopefully this makes sense in understanding some of those rules at a fundamental level. We're not going to extend this and do really complicated probabilities, so don't worry about that. You should just have a general working knowledge of some of these concepts, so that way you can apply them to some of the basic problems in the book. And then when we get to talking about inferential statistics and bring up probability, hopefully that brings you back to this and we understand a little bit about this to help us out. Okay? So we'll leave it at that until we get into some of the inferential statistics a little later on in some of the other chapters.